Hello, hello. Good morning, evening, afternoon, wherever you are in the world. Happy Thursday. Thank you so much for making time to be here with us today. My name is Heather Grant. I'm one of the community admins here at the Maintenance Community by Upkeep. Thank you once again for taking the time. If you're not already a member of our maintenance community on Slack, I will drop the link on how to sign up in the chat. In just a moment, we would love to have you join us. Today, we have Alan Ross joining for a presentation on how to succeed or fail in creating a reliable and safe electrical system. The recording from our session today will be available in the maintenance community on Slack tomorrow, along with a copy of the slides that you see here today. Alan himself is also available to answer questions live in the Slack group. So please feel free to share the recording of this webinar or the invitation to Slack directly with friends, colleagues, or anyone you know who would benefit from hearing some of Alan's expertise. Last piece of housekeeping before we go ahead and get started. Please ask questions throughout the presentation. We'll have a little bit of time at the end of our presentation today to answer any questions. You'll use the chat feature on the right-hand side of your screen there to ask any questions of Alan or answer any questions that he may pose to our audience as we go through the presentation today. Anything we don't get to during our time, we'll make sure to answer offline in the community as well. So please feel free to ask away. That is all from me. I thank you again for being here with us today. And Alan, I'll turn it over to you to get started.
Great. Thank you very much, Heather. So when you do something like this, you have no idea who is behind the camera, right? Who are the people that are listening to this? Because I can promise you, depending upon your role, you're either going to be bored to death, or you're going to go, wow, that makes a lot of sense. And he's one of the brightest and smartest people I've ever talked to in the last week. Or you're going to go, there's something in there and I'm not quite sure how to use it, but I'd like more information. Either way, it's fine. But if you're bored to death, there's something wrong with you, not the presentation. So what I want to talk about is I was the founder of EPRA, the Electric Power Reliability Alliance. We're still trying to figure out what that means. It really was formed because I am a CMRP, which is Certified Maintenance and Reliability Professional. Most of us know SMRP. That's the body that certifies. SMRPCO is the body that certifies, but it's an SMRP driven. CRL, Reliability Web, or the International Maintenance Conference, Terry O'Hanlon's group, certifies CRLs. They both like to think they're totally different, but you know what? I didn't know a lot about vibration analysis, and I took the test, and I passed both of them. But it really does deal with the mechanical side of the reliability world, and it comes out of Society of Maintenance and Reliability Professionals. Ron Moore and Ron is a frequent speaker at a lot of these things. He and I both agree that it should be Society of Reliability first, and then little m, big R, little m, because as you'll see, whether you succeed or fail at creating a safe and reliable electrical system really depends on whether you approach it as a maintenance issue or as you approach it as a reliability issue. So here are the challenges that you must overcome. So this is it. You could stop after this slide and say, yep, we're accomplishing all of that. Or nope, we're not, we're going to fail. So it's that simple. And any one of these could cause you to fail. All of them in combination will cause you to succeed if you take them into account. And that first one is exactly what I just said. You've got to have an electric power reliability mindset. It's got to be about reliability, and it's got to be the system. It's not about the assets in the system. One of the unique things, and this is probably true somewhat of the mechanical world, but there are parts of a mechanical system that can go out and the system still works. Not so with electrical systems. You know, it could be the smallest relay that shuts the system off. It could be a problem in a cable. It could be the transformer, the heart of the system. But it's a complex system. It's power in that feeds something, whatever that is. If you're in the utility world, you're either distributing power, transmitting power, or making power to be transmitted and distributed. And even that is changing dramatically. Everybody knows this. We've got an aging infrastructure. That is probably more critical in the electrical system because the mean time between failure for transformers is almost 40 years. If you're not paying any attention to mean time between failure because the asset you're talking about is 40 years, you have forgotten about it. You haven't done a risk assessment and analysis. So consequently, the aging infrastructure has allowed us to depend on our electrical systems. The average power transformer as of 2016 was 38 years old. I don't think it's going to be any less than that today. And when I say power transformer, every primary feed that you have in industry is a power transformer. Distribution transformers are power transformers. So I'm not talking about the big boys, the GSUs and the transmission transformers. I'm talking about the ones that we use day in and day out, and there are thousands of them. So everybody who uses power to make something or process something or to move something or to provide an environment for data or to run a hospital all has at least one power transformer, and that is that feed. And it's now over 40 years old. That ought to terrify us because they were built to last 10 to 20 years, and we're running them at 40 years, and not everything lasts, particularly electrical system. We all know that we've got this general transformation of knowledge. The old guard like me has a lot of legacy knowledge to pass on, and the millennials are having to learn more than I did and work with less people, less resources, and being told, oh, by the way, I'm not going to let you spend any more. So the idea of generational transfer of knowledge is not coming. It's already happened. And we've had too many retirees to retire with that legacy knowledge. How do we capture it and make sure that which is valued is what is passed on? We are doing digitalization. There was a conference I went to when I was the CEO of a company. That was almost 20 years ago. And it was in New York. And one of the things they told us was digitalization is going to be your future. So, and this was an industrial conference with CEOs. And what they were saying was you better get used to it, understand it, and have people within your organization that run with it. And we're right now in the middle of it. This is not that big of a deal today, power quality and automation, but I'll share with you something that is a case study, and you'll see why power quality and automation is going to be bigger and more important. And even if you do all these others, but you don't get the power quality automation thing right, it will cause us to fail. And then finally, what I kind of started with in the beginning, we can't look at the reliability of the asset. We have to look at the reliability of the asset as part of a system. The system, electrical system, is designed to run something. That something is a productive asset or series of assets. And you can shut the whole plan down by having one primary go out. Yeah, but we've got a backup. Well, yeah, but if you're running two transformers at 80%, you no longer have redundancy. And even if you had a third transformer in there, you still may not have redundancy the way it's defined. There's a thing in data centers, 5.9 reliability, 99.999%. That really came out of some reliability work done with Nolan and Heap, came out of the airline industry where, they needed to make sure airplanes don't fall out of the sky. Well, now the data center people are saying, we can't have downtime. So everybody, said, no, it's going to be 100%. There is no such thing as 100% reliability. So here's what the data center world did. They just put redundancy in place. So they got a 95.5% asset that's reliable and a 94%. And they say, yeah, but if you combine them, but you see, if one of them goes down, you're no longer reliable. So you're not 99.99% if you depend upon redundancy. So probably not new to many of us. This is the definition of reliability. The apparatus, the machine, and I highlight system, to consistently perform its intended or required function without degradation or failure. If you're in the electric power or reliability world, you know that that's already an issue. Degradation or failure is an issue, and what we have in most of the maintenance world is a maintenance Mike, the guy that can go in and fix machines. Trust me, when your 38-year-old power transformer goes down, maintenance Mike is going to be useless. All of your electricians are useless. You've got to be able to replace that asset, and you should have been thinking about replacing it before it went down, because most people think, yeah, well, we'll buy another one. We know you're not going to get a spare. Might be $1.2 million asset, $1.2 million. Nobody's going to let you have a spare, right? So consequently, you got to start thinking about life cycle on that. And probably, in fact, more so today that asset is not going to be able to be made by the same company that made it in the past. So you're going to go to somebody to specially bench build an asset for you. And what they're going to say is, well, that's great. It'll take 6 months and it's going to cost this much. And you're going to go, well, I don't have 6 months. And it's happening every single day. So engineering, reliability engineering, which is, I'm a mechanical engineer, but I've been playing a reliability engineer on TV or on this for a long time. So I've taken the IEEE, I'm a member of the IEEE Smart Grid and love the fact that we are really big on standards. But if you think about it, they focus on engineering is the science of measuring the ability of an asset or system to function properly. Do we really do that in the electrical system? I have yet to see anywhere that it's done in the electrical system. So when you think about all of the things that you've got to avoid, let's go to them. The things that you can say, hey, I'm going to avoid those. Now I can start working on the positive side of this. The first one is you can't think of maintenance management. When you're in the maintenance department, I can promise you every vice president, president, C-level, plant manager, you name it, above you is saying maintenance is a cost center. What happens when times get tough? Cut costs. The two departments that get cut the most are two departments that shouldn't get cut. One is sales, the other is maintenance. So they kick the revenue part of it and they kick the cost part of it. But that is the short mindset thinking that we have when we think maintenance. We think maintenance schedule compliance. Most people don't have a maintenance schedule for their electrical system because we don't want you maintaining everything. We don't want you messing with some of these things. We do want you testing your breakers every 2 years. We do want you to do an arc flash study every 2 years. But that's not maintenance. That is just making sure you're in compliance. Yeah, and as I said earlier, maintenance Mike is the hero. He comes in and he saves the day. You know, the guy that keeps the plant from going down isn't the hero, and he or she should be. Maintenance Mike is just there. He can get it back up, get the machine working. Yay, yay, Mike. And we've thought about the idea of living in a repair environment is our maintenance environment. We've been trying to move maintenance to a predictive. We've been trying to do that for 40 years. I don't think we're very good at it in the mechanical side, and we are awful at it on the electrical side. And here's why. Mean time between failure and mean time to repair doesn't even apply in the electrical system because it's not like, oh, a motor that you say, hey, these motors, the mean time between failure is this many rotations. We should do this at this point. Doesn't happen. As I said, most power transformers are over 40 years old. And we don't really do a spares and MRO-centric approach to the spares part of electrical system. We may have some spares, but I can promise you, if you've got high voltage cables running under your plant to go from your primary feed down to your secondary feed in the plant, nobody's got spare cables for that. You don't even know how to get to it. And you know, I'd be surprised if we have accurate one lines of those anymore. We were at one plant and we showed where the cable went. When the cable company came in to fix a problem with the feed, it was a cable feed, and it was before we could actually detect exactly where it was. Today, you can run that cable length and you can know where the problem is. But we had to dig up cable to figure it out. There were 7 splices that were not on the one line diagram. And of course, it was one of the splices, but there was no spare cable. There were actually a couple of spare splice mechanisms, which is really crazy because what they were saying is, hey, if it breaks, just splice it again. You know what all of these are. These are the things in reliability and maintenance that we use all the time. We know what a criticality analysis is. We're pretty keen on what that is. At EPRA, we're developing a criticality analysis for electrical systems. It is not an in-depth one. It is, let's call it an advanced Excel spreadsheet to determine what quartile you're in on a subjective basis based on the impact of the feed. And so that criticality analysis, everyone's going to understand because it aligns with the rest of the, even IEEE has standards on criticality analysis. So we follow those. But we're used to all of these. Some of it is done in the electrical field, but very little of it is. We don't use risk priority numbers because there are so far in between failures. We don't use reliability-centered maintenance. We've tried to put something in for transformers years ago, and very few people use it. We use much more preventive maintenance than we do predictive maintenance. And we're just now getting to predictive analytics where we're putting monitors on different things. But it's the body of knowledge and the disciplines within the reliability world that we like. They work in there, but here's now the biggest issue that's coming in. Everybody wants to use artificial intelligence and machine learning. I can tell you in electrical systems, I have seen some great examples of machine learning. I have not seen even a bad example of artificial intelligence. I have seen people call artificial intelligence machine learning, or call machine learning artificial intelligence, but that's not true. Machine learning is a subset of artificial intelligence, and I can promise you, you're going to see more and more companies bring in software and systems to try to help you with this. And if you put it into your electrical system, because we don't have good historical data, we don't even have good trending machine learning data, let alone artificial intelligence. So it's going to be a while before they show up. But these are new reliability disciplines. They're not maintenance disciplines. So you're going to see it more and more. And ultimately, what we're trying to do is we're trying to capture people my age who are leaving with legacy knowledge. And we're trying to say, hey, can I take that legacy knowledge and put it somewhere that even though you're no longer around, the machine can make some determinations. You know, one of the things I love about engineering is we extrapolate and interpolate. So extrapolate, you give me 5 data points and I'll tell you where it's going. I may not be perfectly right, but at least I can show you a trend analysis. You give me 7 data points and I've got even more. You give me 1,000 data points, and I can probably extrapolate exactly where things go until you get to an aging part of it where I will begin to dip that curve upward and say, no, your failure rate's going to increase just simply because of aging. We're already there. So the idea of ML is spreading, but it's not really been done in the industrial world yet. The best I've seen was Southern Cal Edison's replacement of their distribution transformers based on machine learning concepts. It saves them millions of dollars every year. Brilliant work, but if they'd have had better data for the last 20 years, they could be even doing better things with it. These are the disciplines, and we're going to do a poll right after this. So Heather, if you could get ready for that. But here's all I want to point out on this, because this one we could go the entire time on it. But when we look at things from a reliability, I just took to technical engineering, that's usually in the plant, maybe your E&I guys, your electrical and instrumentation, it could be electrical engineers, but that person is typically looking at these 4 areas of how we look at reliability from an asset class standpoint. All reliability begins at design. I don't think anybody disagrees with that. I think Ron Moore is one of the gurus. He's one of our fellows. I know there's a lot of them. Jack Nicklaus, not the golfer. We kind of evolved, landed on the fact that it starts at design. I know Terry O'Hanlon from Reliability Web is passionate about that. But the design of an asset or the design of a system. But we're typically working in older systems and older assets. So we don't get to redesign it, but we do get to design the new asset coming in, but it still begins at design. Then we operate it. How we operate it, how we maintain it in operation, whatever it is, all of these design, operations, maintainability, and life cycle, they're all part of what we look at when we look at it under different disciplines. When you look at it from technical engineering, you're typically looking at specification, design parameters, and here's the requirement. Purchasing has now ruled. Back in the day when I was a young engineer, the pendulum was we ruled. We got what we wanted. We go in a plant, we'd say we need this. We would work with the manufacturer. We would select one and say, yeah, we need to have this. Yeah, what do you know? And they would give us information. And then procurement would just give us a purchase order. And then we saw the pendulum start to switch. And it was like, well, we got to be careful. You got to go to bid. Now it's out over here. You're not even allowed to talk to the manufacturers. They've got to bid on the specifications. And see, in the old day, I could actually learn from a manufacturer, say, you know, Alan, that's the old way we did things. But there's new insulation methodologies. There's new ways of doing bushings on a transformer. And I would learn from them, change the specification. Can't do that anymore. So I put the spec out. It's not right anymore. And I get the lowest bidder. That's what you get when you do nothing but technical engineering. So we bring in the asset management people, the ISO 55,000 people, right? What are they looking at? They're looking at a balance sheet. What's the return on this investment? What's the impact on the system financially? How do I get maximum asset utilization? You know, what's the lowest maintenance cost that we can do here? You know, how can you make sure I have the lowest cap costs? I want to keep my capital costs low. We don't have any capital costs this year, so spend more on maintenance, keep it going. And you see, you look at the asset manager discipline, and you're going to look at the same thing differently. But here's how we look at it. We should be looking at it from an operational functionality. How does that asset or system work to keep the product flowing and to keep the steel doing whatever it's doing? But what is the impact of that asset or that system on the production system? And that's what we in reliability should be looking at. If I remember when we talked about reliability engineering, looking at the measurement of that. If we can measure it, even better. But what if we can't? What if it's subjective? And here's it's no or go or no go. If the system goes down, does the line go down? Yes. How much does the line produce a day? $150,000. How many days is it going to be out if the transformer is down? Oh, it's going to be out 6 weeks. Do the math. What happens if it's a breaker and you have spare breakers or they're easily available? Now you do the math. So there is ways that we can look at it, but we need to take control again of the whole design, operations, maintainability of an asset. And then within the parameters, all of that goes there. But that's what we're building, a reliability approach to the design, operations, maintainability, and lifecycle management. There is a place for asset management. There's a place for technical engineering. And as a team, they will come up with the best financial decision that will meet the technical specifications. So purchasing feels good about it, procurement feels better. And then the reliability people can say to the plant management, to the people who are producing something using those assets, hey, we've given you the best possible system that you can. That's what we need in electrical systems. I'd like to do a poll now. Heather, if you could pop that poll up, and then I know it takes a few minutes for people to answer, and then you have to share those results with us because we compile them into it.
Yeah, we'll do. So the poll is live in the poll tab at the top there. So okay. in order for everyone to see the results, you'll be able to see them once you start submitting your answer. So go ahead and submit an answer, and then I'll read out what that looks like.
I don't see that, Heather. So when you have an answer, let me know, and I'll.
Will do.
I think we should sing a song when we do the whole. That's the old Jeopardy. Yeah. And then when we get to the end, you're going, the poll is over. I told them they wouldn't be bored. We ready?
Let's give it another minute or so. We haven't had too many answers. Still waiting for a few more out there.
And people are thinking, they're going, wait a minute, I don't even, if you don't know the answer to the question, then you're going to fail this, either succeed or fail. If you don't know the answer to this one, you're going to fail, because the answer to this one is critical to the success or failure of a program, because that's the other thing. Everything I'm talking about is programmatic. Now, by that, I mean, it is not going to be done overnight, and it's not going to be done by one person or one department. It is programmatic, and it's going to depend upon a committed team to impact the overall reliability of a system. New systems are easy. Design them correctly. And even in that, don't let it, designed by the cheapest. The whole wind farm business that we've got. I would venture to say half of the wind farms were made incorrectly, were built incorrectly, because they were built by people who got money from the government, and they built them. They didn't have to operate them, and they didn't own them. So they sold them to the utilities, who had to have more wind farms, and now they got to maintain. They then outsource it, and somebody's got to maintain them, and they got the wrong assets in a system. There are more bad transformers at the foot of wind turbines than anywhere else. Why? Is because they took step down asset and turned it into a step up asset. And it didn't work. And so consequently, they're struggling. And there was a quick fix, but it cost about $3,000 per transformer to fix it. And for a $15,000 to $16,000 transformer, nobody wanted to spend $3,000 more. Today they do, because they realize when you mess a $3 million turbine up, somebody pays the consequence. We ready? I've stalled enough.
Yeah, good one. We're at about 30% for we are well on our way, 30% for we are just beginning, 30% for we know we should, and then the remaining 10% at no program.
Well, then you're my heroes, because then we asked in 2019, we do a thing called the Electric Power Reliability Summit. At least we did in 2019. We didn't get to do one in 20, and we don't get to do one in 21, but we will do one next year. And we asked senior reliability, corporate reliability people, do you have, I've done it again, Rachel, I'm hitting the wrong button, but do you have the same question that you got? These were the answers in 2019. You all are 30%, 30%, 30%, and 10. Thank goodness we moved from that 50%. So we asked the same thing kind of on a continuous basis. So your information will go in and it will then adjust. And now you can see we're adjusting up. You as a group are still better than the group that are here, but we are well on our way, or we are just beginning. That ought to be 90% of the people, or you're going to fail because the machines will fail you. The system will fail you. So if you haven't started, you need to make a case for starting. The reason we exist as a not-for-profit at EPRA is to help practitioners get the resources they need and to take a third-party peer-reviewed approach to what electrical system reliability should look like in industrial and commercial applications. And then that way, it's a little bit of a bully pulpit. So becoming a member of EPRA gives you the ability to go to your bosses. But look at the difference. And I can promise you the difference is knowledge. It's knowledge. People know better. And as they know better, they're going up to their bosses and saying, hey, we should have a program. Now, when I say program, EPRA doesn't sell a program. We don't do the programming. I really don't care where you start or how you start, but it will always start with a team. You will start with a team and you will evaluate what ifs. And you will start with your one-line diagram and you will follow a set of rules like NFPA tells you. The National Fire Prevention. You should do an arc flash study every 2 years. Very few people that we talk to or that I talk to, and I'm talking to our choir here, right? Very few people actually do it every 2 years. And you know, it's a major deal to do that because it's dangerous if you don't do it. And most people don't have the expertise in staff. So there are a lot of people, professionals out there that will do it, document it, and let you know where your safety issues are. So it all starts here, right? It all starts at a one line. Even here, you have accurate one lines. We had a hospital that we were talking to 17 facility managers for this major international hospital. And we asked the question, do you all have access to your accurate one-line diagrams? And about half of them raised their hand. This is a hospital. About half of them raised their hand. I don't know what that meant for the other half that didn't. But when we asked that half, keep your hands raised, how many of you have added new equipment into your system within the last 2 years? Almost all of them did. It's a hospital. They keep buying these machines that are expensive and radiology departments, et cetera, et cetera. How many of you have updated since you've done that? None of them raised their hands. You see, there are certain things that if we follow the standards, if we follow the rules, we're well on our way. But even in that, it's just going to really point out bad actors. And these are the bad actors, because when you look at a high voltage system, it's true all the way down to medium voltage. But once you get into the high to medium, medium to low, now you're going into motor control units and variable speed drives and et cetera, et cetera. But when you get right down to it, it's these major asset classes that make up a high voltage system. That relays and protective equipment is now also battery backup systems, a lot more things happening there. But when you look at the significant issues that you've got with each of these, transformers, they have not been maintained. You got dirty oil with moisture in it. You know, the majority of transformers that one of our members tests, and they test over 100,000 industrial and commercial transformers a year. The majority of them have unacceptable levels of moisture. Think about that. Unacceptable level of moisture. It's poor maintenance. Get the moisture out. Moisture kills the paper. Life of the paper is life of the transformer, et cetera, et cetera. Cabling. Boy, as I said, you got splices everywhere. And once again, cabling is right along with transformers in terms of aging, and they don't last forever. We see more water trees now than we've ever seen, and they tend to happen at deterioration of and it's not like you don't have rotating equipment here. You've just got a buried cable, but it deteriorates over time. The insulation sheathing deteriorates. Splicing is a major issue where you get problems. The breakers, again, it is aging of breakers and the lack of testing. There are protocols on breakers. We've got a lot of new gas breakers coming into the marketplace that even those SF6 gas breakers are now becoming obsolete because EPA doesn't like it. And we're coming up with new gases that are much more inert. IEEE is doing some standards work on that as we speak. But breakers suffer some of the same problem. And this one is not so much that you got aging, it's solid state. It's changing the nature of the system when you go from an electromechanical system and you start adding solid state relays and protective equipment. And it's here that power quality has the greatest potential for showing up. And when you do something positive for the system and you think it's going to work, and what it creates is a power quality issue. And when you put them all together, these are the issues that if you can begin to address them, you'll begin to have a successful electric system. If you don't, you'll have a one that fails. And any of these asset classes can fail you. And as I said, you put solid state into an electromechanical, it changes things. Here's another reason that power quality is going to be an issue. This was how our electrical grid works. Generation, whether it's coal or hydro or nuclear or whatever, creates power. They get it stepped up and it goes through the high voltage lines all across the country. And then it gets distributed, it gets stepped down. So these transformers along the way and everything built into the system is an up, step down. You create it, step it up to the lines, step it down into distribution, which either goes to an industrial facility or into a community distribution system. And you can just see the difference between the volts. And that's what we're trying to do. We're trying to transmit it at high voltage, low ampere, and we're trying to use it at higher amps, lower voltage. That's our system. Unfortunately, this is our new system. This is not happening. This has already happened. It's step everywhere. You've got generation out in the market. Electric vehicles, electrification of transportation is going to change the way the entire grid works, because you're going to have all of these batteries running around sucking power and driving people, and then they're going to come home at night. And when we think the power stops and the air conditioners go on because it's hot in Houston, but everybody plugs in their high voltage need, they're going to need a much quicker charge. The drain on the system is going to be tremendous. But you know, you've also got wind. When the wind doesn't blow, what do? We're not building any more nuclear plants. We want to get rid of all the coal plants. Thermal, biomass is growing, but not going to do it. Solar power, all of this creates a step everywhere grid. And you as an industrial plant or a data center, you're in the middle of it. And a lot of the changes that are taking place are going to give you less power quality. It's not the same power coming from a solar power station as it is a wind power station. And the utilities are responsible for getting it to you. They're not necessarily responsible for what we call clean power as much anymore. And you expect when the wind doesn't blow that the utility is going to have some backup system that's going to work. We use a lot of gas systems for those now. Those that oppose gas system because of fracking, if the cost of gas doubles, it's not going to even be close that you can build up all these, they're called peaker plants. When you need them, they're up and running immediately. When you don't need them, they're just on a slow burn, but they're ready to go. You try to take a nuclear plant from out to go. It's months, not weeks. Coal plants, it's weeks, maybe even months. these bigger plants take a lot of time to be able to get back up and gen power. And the wind and the sun don't give preferential treatment. That's why we build so many of these wind farms, places that the wind is always blowing, and solar power where the sun is always shining. So I was asked to do an article for Efficient Plant magazine, and it was on power quality. And I knew a little bit about it. I knew what this is. I knew the problems with power quality. But what does this, excuse me, have to do with this? Well, it has everything to do with it, because you're going to get a lot more harmonics, not maybe spikes and sags when the power goes out, but yes, you will have more problems with continuous power flow when they're switching to a gas peaker plant from a hydro plant, excuse me, from a wind power, because the wind isn't blowing enough to be able to gen. So the utility's got to be able to balance all of this out. What we're really going to see a lot more of is harmonics. We're going to see a lot more problems, and that's that red line at the bottom. And you're going to get a lot more poor power quality as a result of harmonics. It's already happening. And for the most part, it's not a big deal until this happens. If you have a problem, and this is 2001, think about this, the EPRI study, not EPRA, we are EPRA, they're EPRI. They are, the utility industry pays money to have this group study a lot of different things and do research. So they looked at the 3 sectors of the US economy that are sensitive to power disturbances. Now that's poor quality, spikes, sags, all of that. The digital economy. Oh my gosh, I just got through saying the entire economy is a digital economy. Everybody's digital. Continuous process management. So if you're running any flow through anything, so it's whether it's rubber or clay, anything, and you're processing it, power quality issues will affect you tremendously. You run a steel line, have your furnace transformer melting all of the steel, then it goes through secondary transformers, furnace transformers, and then it goes down to a line, and it's either rolled or it's turned into rod or whatever. If you shut down power on that because you didn't take care of your power system, it's millions of dollars to clean up that line. We have a customer of ours from years ago in the aluminum business that lost their aluminum bar plant because they lost a transformer. The plant shut down. 1,400 people lost their jobs. They were not going to rebuild it. It was life-changing for many people. And then fabrication and essential services, wastewater treatment, anything that does with mass transit, gas, utility pipelines. This is not about cybersecurity. It's about power quality. And the EPRI study said these are the economies that are going to be affected to this scale in 2001. West Coast, 7.2 billion. Southeast, 7.9 billion. You can read them here. It's a big deal. And we've been trying to tell people about it, but aging infrastructure, it hadn't happened yet. I don't know why you're bothering me with that. Nobody's wanted to have any money for that yet. Why don't you just put more in the maintenance budget? Yeah, try to buy a $4 million transformer overnight out of your maintenance dollars. Doesn't happen. And so consequently, the scope of the problem is big. This is a case study, a true case study, that shows why this whole move to a solid state versus electromechanical is important. There's a dairy storage facility, and what they did was they produced food in one side of their facility, and it was food that had to be packaged and flash frozen. So it had to go from wherever they made it, cooked it, packaged it, and it went on trays, and they put it in these flash frozen freezers. These weren't the exact freezers, but they had racks, lots of racks. Well, that at the bottom rack, it's going to be colder than at the top. So the way they managed it was manually. They would check the temperature, and then they would rotate, and they would pull out and rotate. They had waste. They had some of them that did, they couldn't flash freeze. It wasn't, they tried to ship it. It couldn't. It suddenly was not any good anymore. So they had a lot of waste and spillage and problems. But that's the best they could do. So somebody came along at one of the big freezer companies and said, we got a better way. We will put these in, and we will have the fans, everything will be regulated. And when we see that it's colder on the bottom, we're going to change the fan to move cold air to the top, and we will keep everything within the regulated temperature. You will not have any more lost material. You will have it be safer. It's a better deal. Everybody loved it. So imagine this whole huge line or lines of these storage units. But they started, when they installed them, before they started actually using them, they started failing. And so they got old storage. I found later that they didn't get rid of all the old storage facilities. They were doing line by line. But the very first and second lines were beginning to fail randomly. They didn't know why. So of course the suits come in and everybody's trying to do something. And the C-level people at the company that bought the freezers is, you're going to take them back. We're going to blah, blah, blah. So potential lawsuits, big time. So an electrician on the second shift saw these suits over there working at the control panel and arguing, and everybody was trying to figure out what it was. He came over and he said, "What are they doing?" And the guy running it said, they have problems with these new freezers. They keep kicking off. We don't know why. And the electrician says, "Well, there's always been harmonics in that feed from that primary transformer or secondary transformer to these lines. There's always been harmonics. You should check that out." They check it out. There are harmonics in the line that had never bothered the system before. And it now bothers these very solid state, very nanotechnology and microtechnology controlled, and a control system that's one person working at the control systems, watching red lights. That's all they were really doing. But the guy said it's harmonics. They put in a $1,500 controller transformer. This was $1 million. It was less than $2,000. And it took the harmonics out, and they ran, and they run to this day. It was a better solution. But think about it. If that legacy person, electrician, didn't know there was harmonics, they might have spent millions of dollars sending stuff back. These are some of the references that you can reference about power quality. I don't seem to be one that I want to promote IEEE, but I love IEEE. No one ever got fired by following IEEE standards. People get fired when making their own standards. You're listening to the standard that the vendor gave them. Well, that's the vendor standard, but does the vendor standard align with the IEEE standard? And the head of member services for IEEE is not even an engineer, yet she is a member of IEEE because of the value that she brings and sees from the standards that they do, and vice versa. And I'm not an electrical engineer, I'm a mechanical engineer, but I get to play with the leadership in the PES and smart grid and all that. We believe in these standards. There are some great ones that are, and if you see, it was 2005, then 2014, then 2017, and you start to see IEC and IEEE trying to align together. One of the best is, of course, NFPA. Following their standards. Again, nobody ever got fired from following NFPA regulations or standards. With that said and done, I have come to the end of my presentation, and I am open for any questions. I don't know how they come across. I haven't seen the chat, so I haven't seen any questions, Heather, but if you could translate for me, I'll do that until you tell me you have no more.
Definitely. So I see we have a couple people typing. We can pause there. I actually have a quick question for you, kind of pulling everything together from what you shared today. What would you say is the biggest obstacle to electrical system reliability? Is it aging equipment, lack of buy-in, misunderstanding, or misalignment, or what's kind of the biggest obstacle that people face in achieving this electrical system reliability?
Complacency. It's lasted so long for so well without anybody doing anything. So why are you messing with it now? It's complacency, which there's two parts of complacency. Ignorance means I don't know that there's a problem, okay? They should now, nobody that listens to this has no excuse for, they're not ignorant anymore. They know that there's the problem. The second one is there are no easy to implement programs. That's why EPRA was born. We have peers who are working groups that are creating accreditation and certification so that we can certify somebody, like there's a certified mechanical and reliability professional. We want a certified electrical reliability professional, same thing. So I think it's complacency. It's never been a problem before. Why mess with it?
Awesome. We have two questions in the chat now. One is a maybe more simple one. Are the IEEE standards available online?
IEEE standards are available. You do have to be an IEEE member in order to get them, or you just pay a higher price. Even sometimes I have to pay for the price. But yes, they are online, IEEE.org. Very confusing organization. But they have societies. We're part of the Reliability Society and the Power Engineering Society. But they have some. There's one in here I did not mention, power electronics. That's what I'm talking about when I say the new solid state. That is power electronics. Absolutely, it is a big issue. Do I see any impact of these with the reliability of the whole electrical system? It is the number one. That's the place where power quality, it may not let you down, it may not fail, but it doesn't deliver power quality when you start putting these in there. So absolutely, it is a huge issue. Now, here's the problem with somebody like IEEE. You do have a power electronics society and you do have a power energy society. They tend not to work together, but we have started to work on an interoperability of standards. How do we bring standards that apply to you to standards here? That's a great question, Matthew. And yes, yes, and yes.
Awesome. I still see a couple of people typing, but you did just answer for Matthew. So next question here just came in from Ahmed. I think you're probably looking at them now, but yeah, in your experience, how many numbers of transformers have failed before those 38 years? Or if so, what was the reason for it happening?
Here's the thing, the annual failure rate of transformers in North America is 0.03%. 0.03 catastrophic failures. How many of them failed and didn't get reported because it wasn't catastrophic, but it failed the system and shut down a line? We don't really know. We haven't kept good statistics. Doble probably has the best statistics of anybody about failure information, but it's very, very low. However, it's also increasing incrementally, and it's now no longer just about did it fail, but can it handle the power electronics you put into the system? So yeah, it's a very low failure rate. The bathtub curve for, this is another one. The worst time for a transformer is the first time that you load it, right? Day one, the infant mortality of transformers is high. The insurance industry says the first year is the highest rate of failure of transformers. So, and then it just goes, it goes way beyond the 20-year life cycle. Now we're into the 38 year before you start to see the end of the bathtub curve go up, okay? So that's where it is. We started doing research with FM Global and Chubb Ace Insurance. And as we did the research, what they told us was it wasn't 1 year anymore. Transformers were failing in 10 years. The early infant mortality rate for transformers is 10 years. That is scary because what they're saying is, you know, you used to be able to get 1 year out of it. Now it's steady state, no matter how you load it. Now they're saying you have to load it differently, even within the first 10 years, to know that you've got a steady state system. They're not made the same way. In your experience, how many numbers of transformers? Oh, no.
That's one I just asked.
Oh, and number one reason transformer fail, number one reason is an anomaly. It is an upline or a downline fault, something that backs to the transformer and causes the transformer fail. Obviously, the biggest anomaly is a weather anomaly, lightning. You can put lightning arresters, and you know, I've seen places that they put so much lightning arresters, you think none of it can get through. They have 1 billion lightning strikes in Florida every year. I don't know if that's an accurate number, but it's a lot. And they're trying to put substations where they haven't had any. I would put a substation where lightning hit, because lightning never strikes twice, right? But it's that anomaly. But why does the anomaly fail some but not others? If the oil is kept dry and clean, the paper is going to last a lot longer. Moisture in paper reduces the degree of polymerization. Moisture in oil reduces the DP of paper. When the paper DP reduces, guess what? The life of the transformer is over. So the life of the transformer is the life of the paper. The cleanliness and the maintenance of the oil is the life of the paper. So it's correlation. It wasn't lightning that causes the problem. I have a great analogy. An old man's got a bad heart. He can live another 10 years with his bad heart. Oh, I'm going to be all right, sitting there watching Jeopardy. But the minute that a burglar comes in and he's got to run upstairs to get his firearm, but he dies on the stairs, did the burglar kill him? Did the fire alarm or whatever it was that kill him? Was it the fact that he had a gun upstairs? No, it was the run up the stairs. That was the anomaly event. And that's what killed them. The same is true as transformers. It can go, it can go, it can be fine. You spike it one time, or you unload, suddenly you've got a sag in the line. That's as bad on a transformer as a spike. Why? Because it doesn't know how to handle those power quality issues. Anyway.
I actually have a quick follow-up question from something you just said. You're talking about how the infant mortality for transformers is unusually high, and I have a just question about that. Is there a way to avoid that, or is that kind of just the way it is?
I think the best way to avoid, that's a great question, is if we can build them based upon how we're going to use them as opposed to the lowest price. So the idea is to have much more robust specs. And I don't mean rating specs. See, the ratings are easy to specify, but much more robustness in the specs. And if, for instance, Weidman is the #1 company of paper and blocking in transformers. They sell a product, or they use a product that's made by DuPont called Nomex. It's going to increase the price of a transformer anywhere from 10% to 30%. I would never buy a transformer without Nomex in it. Why? Because it is the paper that lasts longer, that can take abuse. It can actually, and you put that with a corn oil product, an FR3 or something like that. Now you've done the best, but it's going to cost more money. And the purchasing people are going to go, but hey, according to that rating, I can get that a lot cheaper. And you will probably hit that 10-year curve. If you buy the one that you know is going to have the better, and it's insulation, the oil and the paper are just insulating. There's no moving parts in a transformer if you don't have an LTC. It's moving electrons, right? The magnetic field moving the electrons around. So you shouldn't have any wear, but it is the degradation from moisture and acids and other things that attack the paper that cause the life to fail. So I would just say use thermally upgraded paper first. That's not 5% more. It costs more paper, but it's not going to raise the price of a transformer 5%. Nomex is expensive. I'm not saying use that, but thermally upgraded paper, more and more people are doing it. Why? It can stand heat spikes. You can run the transformer above rating. #1 thing, thermally upgraded paper, and not just Weidemann makes that. A number of people make. They just happen to make the best. I don't think I'm allowed to say that, do I?
Is this an ad? Yeah. No, you guys are sponsored, or? I have another quick question here from Ahmed in the chat. It says, if you're an electrical engineer.
Yes, he can. As a matter of fact, we encourage it now, becoming a member of IEEE, because even that of the Institute of Electrical Engineers, right? That's kind of what we are. But what we have created, we've got so many societies now where you've got a lot of the new thing is we've got a lot of chemical engineers and chemistry people in, because of the makeup of materials in the electrical system. But yeah, definitely a petroleum or any other kind of an engineer. Of course, I think mechanical engineers rule the day, so we're all problem solvers. But that's the beauty of it. More and more today, IEEE is recognizing that. That's why they don't say Institute of Electrical Engineering. They just say IEEE, and it does mean other people. Okay, Ahmed, join them. It's not expensive. And if you happen to be a student, it's free. Or
awesome.
Like $8.
That's all the questions in the chat. I do have one more kind of in my brain
Sure.
that I would love to ask you, while I have a couple more minutes here on the hour. Oh, we just got one more. But who in your opinion is the best person on a team or within an organization to kind of own this electrical system reliability? Is it the reliability engineer? Is it the electrical engineers? Does it need to be a whole new role, or kind of how does that sit in an organization, in your opinion?
We struggle with that, because I think the worst person to do it is someone that, and it doesn't even have to be an engineer. I actually think the best person to do it is somebody that reports directly to plant management and has a leadership responsibility. I don't think it's the maintenance department, though. So if somebody said to me, what do you see the most of? It's typically either the electrical engineer or the E&I folks. more and more, because of the instrumentation part, electrical and instrumentation, you see them more and more ready to grasp the problem. I got to keep the electrical system going, but I'm the one adding all of these new relays, and I see what's coming in and I'm approving them, and I see automation and instrumentation and robotics come in. So if I were to choose, I would want an E&I guy. But a bad E&I guy who doesn't know how to lead is not going to be a good thing. So any one of those that is willing to be a great peer leader, someone who can bring other people and bring stakeholders together, because it has to cross more than one of those disciplines in order for it to succeed.
Awesome.
Okay.
Wonderful. I think we kind of went through this transformer question in our last bit. I think that's all from us today. I appreciate.
I've seen some of critical manufacturing initiative transformers, or one additional transformer, which is sufficient. Yeah, that is okay. When you have it's called a double-ended sub. When you have two transformers that are basically sharing, it's a double-ended sub. It's redundancy. That's great. One of the ways to solve a reliability issue is redundancy. Here's the problem. You now have a power quality. They both react the same way to it. You haven't solved it. They will pass it down line, and whatever they feed is the problem. So you can't make a double-ended sub a double-ended system. No one will let you spend that much money. But the idea, and typically people do it because there is some point in time where you got to run one transformer above rating, and you got to have that backup. If they do it just to have a spare, very seldom do I see that, unless it's a data center. Data centers have to do that. They've got to have double-ended subs. They've got to have backup generation. They've got to do a lot of battery things. Hector says it's a gorgeous presentation. Hector, thank you. I love it. No one said it's boring.
No one did.
Thank you so much, guys. I appreciate it. And thank you for what you're doing. And I guess I'll meet you on Slack, or is that what it's called? Yeah, I can't remember. I'm the generation still trying to figure out how we use social media tools. All right.
Yeah. We'll get you in there. No worries.
Great,
I appreciate your time. Thanks so much, Alan. Thank you, everyone, for joining today.
Okay,
I'll see you.
Bye-bye.
See you next time.